research in physics.
Good morning, everyone. So I'm the chair for the interdisciplinary session, and this year we've got 5 exciting abstracts. 5 exciting abstracts presented for the Undergraduate Physics Symposium. And for this session, our keynote speaker will be Atreya Majumdar, an erstwhile student of Presidency University. He's right now a second-year master's student at the University of Groningen, and he will speak on simulating molecular motors driven only by light. So you will get 25 minutes. When you have 2 minutes left for your talk, I'll give you a sign and then 3 minutes for question and answer. Alright? So
5 minutes for question.
Okay, 5 minutes for question and answer. So can we have a round of applause for
So, welcome and good morning everyone to the Undergraduate Physics Symposium. I am Atreya Majumdar, and today I am going to present my work on simulating molecular motors driven only by light, which was done under the supervision of Dr. Thomas Jansen at the University of Groningen. So now today, all of us have something in common. So the way we reached here is either by train or by bus or by car. And all these things have one thing in common, which is a motor. Now some of you will say to me that I've just walked here and there is no motor involved there. To those people I would say that inside our body, inside our cells, there are motors running all the time that are driving physical processes. Like so there are things like this inside our cell going on all the time, which are like machines moving. So this is going to be the crux of this talk, and talking about molecules that can serve the function of motors. And this is going to be my talk outline. First of all, I will discuss the current state of existing molecular motors. Then from there on, we will move on to our model that we are studying and discuss its working principle, its dynamics, and from considering those points, we will propose a design principle in which we can actually synthesize a molecule. And finally, we will end with some conclusions and future work.
If it's not needed, don't use.
So, what is a machine? Machine is anything that takes in some form of energy and converts that into mechanical energy. So, there are some examples in molecular systems as well that show these kind of machine properties. Like there can be molecular shuttles which is basically nothing but a molecule with a long chain and some rings like this, which can shift from this position to this position. And this kind of system can be used for molecular electronics purposes, where one of them can be called 0 and the other 1, and which can also serve purpose of a qubit, as was discussed yesterday in Amita's talk. So another kind of molecular machines can be molecular motors, where there is using light energy and thermal energy, the unidirectional 360-degree rotation is achieved. And using those kind of molecular motors, even something like a molecular nanocar can be synthesized. Now, if we can control motion in the level of a molecule, we can very easily see that it can have huge applications in the field of drug delivery inside bodies, as well as in fields of nanorobotics or molecular electronics as discussed in this kind of molecular shuttles. So for this kind of work, the 2016 Nobel Prize in Chemistry was awarded to these three scientists, and Professor Ben Feringa here is from the University of Groningen, where I am studying currently. So his work was for this kind of, the synthesis of this kind of molecular motors. Now what is happening here is, using light and thermal energy, we are getting a rotation about this pi bond in the middle, and it involves basically two steps. First of all is the photoisomerization, in which this along this bond, this part of the molecule is getting rotated here, and the second one is the helical inversion. What does that mean? It means that this black part, which means that part of the molecule is taking out of the dotted part is and the dotted part is like sticking into the bone. So what happens in this step is that these two positions exchange, and this is called a helical inversion because basically a helix which is getting inverted, and these steps involve some thermal energy, whereas the first step, as we discussed for the photoisomerization, required some kind of an photonic energy form of some wavelength. So let's look at what kind of energetics this is involving. So in the first step that we had, it was sitting somewhere here, and it had a very high potential barrier to cross. So what we did was we put some energy, put some light energy in it to excite it to its first excited state, and so it can roll down here to this point and come to this conformation, where we see that this kind of isomerization has occurred. Like this is a trans-cis isomerization. But now we are sitting here, and it has a smaller hill to cover, but it doesn't have any kind of excited state health like that. So what it does, it sits here and waits for the environment to provide it with the enough energetic kick so that it goes from this point to cross this small hill. So finally it goes here, and this step happens once more to complete the whole rotation. Now we see that the system was waiting here for some time, and from that we can very easily see that this is the rate determining step of the whole process. That is, this step is taking the longest amount of time. So if we can somehow eliminate this step where some thermal energy is required to overcome a barrier, then we can get it to rotate much faster. Giving some numbers, this photoisomerization takes something about a picosecond, whereas this process, this process of overcoming this potential barrier makes rotation rate to about 1 rotation per millisecond. So if we can eliminate that, we can get a rotation speed of about a picosecond, which means an increment in 9 orders of magnitude. That is a baby crawling to the speed of light. So can we do this? This is the question that we are after. So our plan is to use only light and eliminate the step due to thermal energy. So we need a part of the molecule that responds to light very strongly, and that is called this chromophore thing. Chromophore is a part of the molecule that interacts with light, and as chromophores we are using transition dipole moments here. So how is a transition dipole moment different from an ordinary permanent dipole moment? The transition dipole moment has this property that when you shine light on it, only then those dipole moments are active. Otherwise they are just, these dipole moments are not there. So they are light dependent. And as we can see in this model, two of the parameters that we can play with actually is the distance between these chromophores. We can make the chromophore much farther or much closer, and the strengths of the transition dipole moments, the magnitude of the moieties that we are using as these substituents. And for our simulations, we have attached this to a board surface, and so here it is a very big system if you consider the total number of degrees of freedom, that is 3n minus 6. But we are mainly interested in 1 degree of freedom, that is how this molecule is rotating. So if we look at this whole system from the top, we will get a projection like this, and we define this angle between the blue substituents as phi, our angle of rotation. So as we are interested in this degree of freedom, most importantly, we will treat this one quantum mechanically. That is the most accurate picture. And for all the other degrees of freedom, we will treat them using classical dynamics. And so, as will be very apparent very soon, that the orientation of these transition dipole moments plays a very crucial role in the dynamics that is occurring, because they are responsible for the whole motion. So, this is basic physics, as if there are two dipole moments, u1 vector and u2 vector, separated by separation vector r12, then the dipole-dipole coupling energy is given by this expression, and there are lots of dot products here, which means that the relative orientation of the dipoles have a very important role to play. And in our case, this is basically means that this coupling energy depends upon the rotation angle, because all the other things are kept fixed, only the molecule is rotating. So this is how the coupling energy depends upon the rotation angle of the molecule. And when there is no light shining on the molecule, there are no dipoles and there is nothing. So when we shine light on it, these dipoles get activated, and since this angle is somewhere close to zero, the rotation angle, it is high up in energy. So it will try to minimize its energy and go downhill. And what will happen is, it will do this kind of a rotation thing. That is basically what is happening is, using light, we have actually made these dipole moments repulse each other, and here we get some motion. The idea is to use this kind of dipole-dipole repulsion to actually get the molecule to rotate completely. But this is a classical picture, as we are just discussing forces and energies and repulsions. But we want to treat this degree of freedom quantum mechanically. So all the information that quantum mechanics has is contained in this quantity, the Hamiltonian, or in other words, the total energy. So we will start from there. The first term that we write for the Hamiltonian here is the kinetic energy, and for this it's just dependent upon the moment of inertia of the molecule. The second term is the potential energy, and for this potential energy, it actually depends upon the actual molecule and its microscopic details. But for simplicity, we have assumed a sinusoidal variation, where the maxima corresponds to this kind of an overlapping conformation, where the coulombic repulsion or the steric hindrance is maximum. And this is minimum when it is somewhere in between. That is this kind of it's called a staggered conformation when it is minimum. And finally, we have this dipole-dipole coupling term, which goes as discussed in the last slide. So now let's look at what is happening in our molecule. So in our molecule, there are two sides 1 and 2, and their ground state potential energy variation of with angle is as discussed. And another assumption here is that the excited state potential, first excited state potential energy also has the same variation. Now this is an assumption, as again we have to do time-dependent density functional theory calculations to get an exact picture of what these are. So now this is the case when there is no light and there is no interaction between the two sides. When we shine light on the system, the dipoles are activated and they talk with each other. And this is kind of a perturbation which makes the excited states split like this. So what we have done here is, like, if we start from here and end here, there is a potential gradient, and we know that the negative of the energy gradient is the torque. So what we have done is, using light, created a torque in the molecule that can actually make the molecule rotate. So let's see how we can do that. So we have our Hamiltonian ready. Now we need the initial wave function. So this is the ground state and this is the excited states. So we want the dynamics to start. So if we start the wave function somewhere in this way, there is going to be nothing happening. Like the wave function is just going to move back and forth, no motion. So we want to start somewhere over here. So to do that, what we do is choose an energy which is equal of the laser, which is equal to the difference in these 2 points. So what we do is, like, push the wave function here so that it has a it can move downhill and start the dynamics. But there is a problem with this. You see that if we plot the ground state wave function, it looks something like this. And if we use some energy like this, not only this wave function, but also this part of the wave function will be promoted here, and there won't be any unidirectional motion in the whole molecule. So what we have to do is introduce an asymmetry which localizes the wave function somewhere over here. We do that simply by just lowering the potential a bit, so that it has this potential weight as a lower depth, so that all the wave function goes there. Now we are ready with the wave function, which is localized somewhere over here. Now we also know our Hamiltonian. So this is just propagated using the time-dependent Schrödinger equation. and we use this kind of a numerical integration scheme where we write the Hamiltonian in a matrix form and do this multiplication over and over again to the propagation in time. This is how the propagation is happening. So we start off somewhere around 30 degrees and it starts to move in this upper potential wave and move very nicely until at around 300 degrees. What happens is that the complete wave function gets reflected. So at this point, we don't have the complete rotational motion. And this is very expected because we are only residing on the upper potential energy surface. How can we get any rotation there? We have to go to the lower one so that it completes the whole rotation. So here we will consider the effects of the thermal fluctuations in the system, the environmental fluctuations. What that will do is for the two potential energy surfaces, they will go up and down in time due to the fluctuation, and the wave function at certain instances of time will also experience a lower surface so that it can go downhill from here on and complete the whole rotation. So let's see how we do that. Again, we go back to our Hamiltonian, the total energy, and add to that the energy contribution due to the bath. Now, how do we model that? We linearly couple this energy to the classical degrees of freedom present in our bath. So this bath coordinate means that all the classical degrees of freedom that we have discussed, we have like indicated earlier, like the bond vibrations, like wiggling modes or different torsional modes, these experience the temperature of the system and they fluctuate in some form. So if the temperature of the system was 0, there wouldn't have been any fluctuation and this term would simply be 0. And to model those classical modes, we have used plasma dynamics with a Gaussian white noise. And since these two sites, they are modeled, they experience different environments, the wave functions for these two sites will evolve separately, unlike the previous case where it was just isolated, it was in vacuum. So it had no fluctuations whatsoever. So let's see what is happening. So you can see the two different colors are for two different sites, which are seeing different environments and are evolving in different manner. And so initially it moves very similar to the last case, and something different happens when it comes to the end. So in the last case it completely got reflected back, but now it is going to the other end and completing the whole motion. Because now part of the wave function went to the lower energy surface and it completed the whole rotation thing. So this is for one realization and this is for different disorder realizations. We can see that same qualitative thing is happening, and the wave function is moving initially in the same manner, and when it is going to the end, a part of it is getting reflected back while a part of the wave function is completing the whole rotation. So we see from here that the rotation is actually happening. This is the point when this happens, that the part is crossing the 360 degree and coming back here. So we see that the rotation is happening. Now we want to quantify it, like what kind of time scales it is taking for the rotation to get completed. So we see that it starts around 30 degrees and then it goes away from there, and only when the rotation is completed does it come back to the 30 degree. So if we look at the wave function at 34 degrees, we see that with time it is falling because the wave packet is actually moving from there, and only when it has completed the whole rotation and come back to that 34 degrees is it rising again. From that we know that the time scale of the whole rotation is about 250 femtoseconds. And so now we know that it is possible. We would like to propose some design principle. First of all, the molecule must be chiral, which means that chirality means that a molecule has a preferred orientation, that it wants to rotate in a certain direction over the other. So if we shine light on it, we will get unidirectional motion all the time, that it will rotate in either clockwise or anti-clockwise. Secondly, it must have some rigid connections, that is to say if it has flabby ends, like flabby substituents for these blue, red and green, then it will incur friction from the environment and that will slow down the dynamics even further. And lastly, the choice of the chromophore, the part which was responsible for the transition dipole moment, is also very important. For that we use this body pi dye family, which is this kind of a system. We choose this because it has a high dipole moment of about 8 dBs, high fluorescence quantum yield and low Stokes shift. So this is the molecule that we propose. Here the middle bond is the middle separating part, and this is site 1 and site 2. So here this blue part, this thing with the blue thing is the body pi dye that we discussed, and it has like this kind of rigid connection which prevents the flabby ends. And it has also chirality property by just introduction of a methyl group somewhere here. And so this is in this work we showed that it is indeed possible to make molecular motors which is driven only by light and get a rotation time scale of the order of picosecond. And finally with that we proposed a design principle by which we can actually synthesize a molecule.
So you have 2 minutes then.
So for future work, what needs to be done is if we do DFT calculations on the molecule, we will get a more realistic picture of the potential energy variation with angle, which we had taken just to be a sinusoid. And for the excited state, we have to do time-dependent thing for that. And finally, the most I would say challenging part would be to actually synthesize this molecule in lab, because till now everything was in the computer. We see theoretically that it is possible. Now we have to look into the synthesis of the molecule and also we have to characterize it. That if we synthesize this molecule, is it behaving like the way we are expecting it to be, or there is some other factors that we have not modeled in our system. So these are the people who I would like to thank for this work, especially my supervisor, Dr. Thomas Lakurianson. And this is a program I am in currently. So if any of you wants to talk with me about this, I am available after this session. So this is a thank you in Dutch. So this is I think better. Thank you.